This is homework problem HRW99P036. It says a 0.2 kilogram puck is initially stationary on an ice surface with negligible friction. At time t equals 0, a horizontal force begins to move the puck. The force is given by this function. Notice it's a function of t, I hat, with force in newtons and t in seconds, and it acts until its magnitude is 0. Remember that the I hat just tells you that it's in the x direction. Okay, what is the magnitude of the impulse on the puck from the force between these two times? Okie dokie. Well, I know that the impulse on an object is equal to the integral of a variable force as a function of t dt from initial time to final time. So all I have to do is plug that in. So for this particular problem, the impulse is going to be, well, we're going from t equals 0.35 to t equals 1.3. That gives us our limits. So 0.35 seconds, 1.3 seconds. The function of force as a function of t is this thing right here. So we've got, let's see, we've got 11.5, oh, come on, 0.5 minus 2.6 t squared dt. Okie dokie. That is a nice polynomial, so when I take the integral of that, all I need to do is bring the variable up by 1. So I have really 11.5 since it's all alone. That's really like 11.5 times t to the 0th power. So what I end up with is just t. And then I divide by the new exponent on t. The new exponent on t is 1, so divided by 1. I'm going to leave that off. I don't really care about that. Alright, then I got 2.6. This was t squared, so it's going to become t cubed, and then I divide by the new exponent. And I do that from the limits of 0.35 to, I always forget the upper limit, 1.3. Alright, so now I just got to evaluate that. I'm going to go full screen at this point. Okie dokie. So remember, you always evaluate top number and then minus bottom number. So, you know what? Let's just use the space. Use the space! Alright, so if I evaluate this with the top number first, remember you put the top number wherever t appears. 2.6, 1.3, that gets cubed over 3, la-di-di, minus, do the same thing but with the bottom limit. So 11.5, 5. Whoops. Yep. And divide by 3. Doot, doot, doot. I'm going to put that whole thing in my calculator. Pause this for a minute. Alright, and I got 9.06. 9.06. And this is an impulse, so that will be in the units of momentum. I'm going to use Newton seconds because it's my favorite. Let's go check. Yep, 9.06. If you use this, if you do this and you come out with some number and you put it in and it doesn't come out right, something is probably going wrong in your calculator. I love my, and I've told you guys this before, I love my Texas Instruments TI-30X2S because I can type this in literally, like push the parentheses button, literally type this in, and it will work. You need to make sure that you put parentheses where you need parentheses. In this case, like here and here and here and here, or it's just not going to work. Your calculator very strictly follows order of operations. So if you're typing something in and it follows the order of operations to give you a wrong answer, there's a different way you need to type it in. Alright, let's look at B. What is the change in momentum of the puck between t equals 0 and the instant at which f equals 0? Alright. Remember, change in momentum is just another word or phrase for impulse. So we're really asking the same question as A, but with a different limit. So for this one, our limits are going to be from 0 to the time at which f equals 0. Well, we need to find that first. We need to find out when f equals 0. So I already know that f... Ooh, my sleeve's in the way. I already know that F equals, what is that, 11.5 minus 2.6 t squared. I just need to set that equal to 0 to find out when force is 0, so that I can get an answer. Okay, so divide both sides by 2.6. And then, so that'll go away. And then I'll square root both sides to get t squared. Okay, so if I do all that, I end up with that the t when f equals 0 is, hang on, I gotta hit the square root button, 2.10. I notice I'm only going to 3 significant figures because that's what they gave me, 2.10 seconds. All right, so I do the exact same thing as before, but now my limits are going to be from 0 to 2.1. Okay, so instead of 0.35 to 1.3, I'm doing 0 to 2.1. This should be a larger number. I'm going to go full screen now, and unfortunately I need the next page. Ugh. It's exactly the same thing here as here. We're just changing, this is going to become 0 and this becomes 2.1. The evaluated integral is the same. So this is the same, I just need to replace these numbers here. Okay, and I'm going to do that on the next page. Okay. Alright, so I'm trying to do 11.5 t minus, and see, this is why I hate going to the next page because I can't remember, 2.6 t cubed over 3, 2.63 cubed over t, 3, 2.6 t cubed over 3. There we go. And I want to go from 0 to 2.10. Okie dokie. So again, do the top one first. So 11.5 times 2.10 minus 2.6 times 2.10 cubed, all of that over 3. Now what I should do is this minus the whole thing again with the bottom one, but look, the bottom one is 0. So I'm going to have a 0 in this term and a 0 in that term. Basically it's all 0. So it's all of this minus 0, which means that I don't really care about the second part. All I need to do is put the this is all impulse, by the way. All I need to do is put this in a calculator, and when I do that, I get, looks like 16.1 if I round to 3 significant figures. And yep, that is what I've got, 16.1. Now they have kilogram meters per second, but remember that's the same thing as Newton seconds, so we're good.